Good morning, guys. Hello, am I audible? Guys, hello, am I audible? Students, am I audible? Hello, guys, am I audible? Hello, hello, guys, am I audible? अरे somebody respond यार,
Yes.
come on. कब से चिल्ला रहा हूँ मैं? Am I audible? सब लॉग इन करके चले जाते हैं क्या? Okay, is this OneNote page visible to all of you?
Yes, sir.
Okay, so we'll finish off with unit number 5 today, and that is the two things that are remaining. One is called as a photovoltaic cell, or also known as the solar cell, and the other one is called as the optocoupler. So let us start off with solar cell. So all of you know that solar energy is a type of energy which is non-conventional, and which really is the energy source for the future, unless and until it is adopted by everyone. At the same time, um, the efficiency of the solar cells uh, is continuously improving. So this actually will be one of the possible candidates as source of energy. The solar cell or solar energy converter, it is also called as solar energy converter. It is essentially a large photodiode. So it is a large in size actually and specifications also. Large photodiode which is designed to operate as a photovoltaic device and to deliver as much power output as possible. So in case of our photodiodes, that is the reason why we covered photodiodes earlier. So photovoltaic cell is essentially a large photodiode, but here its function is to generate as much power as possible. Okay. The surface of the solar cell is much larger. So surface, what is the basic difference? Surface of solar cell is much larger then photodiode. Now this is basically designed to provide maximum output current. That is basically the design. Let us see the characteristics of this thing. So this is current, milliamperes. This is voltage in volts. So 10, 20, 30, 40. So it depends on light intensity. Guys, am I still audible? Hello?
Yes, sir.
Yes, sir.
So this is dependent on the light intensity. These curves. So what do you see from here? Light is incident and it generates current. Okay. But as you can see, as you draw more and more current from here, from this device, what happens? So here up to this, let us say up to this point, Up to this point, it is supplying significant current. Okay, but if you short circuit the solar cell, in that case, as you can see, which is highlighted. So if cell is short circuited, that is output is um, V out becomes equal to 0, then the output current is almost, let us say, 65 milliampere. But if you look at the power that is being delivered, please remember that this is supposed to deliver power. So what is the power that is delivered when the current is 65 milliampere, but voltage across it is 0? That is, it is short circuited. The power also is 0. All right. So I can say that you have a specific point where maximum power is delivered. So this point, for example, so voltage across it is nearly about 5.5 volts, 0.5, sorry, 0.5 volts, 0.6, 0.55 volts, and current, it is supplying current also. It can supply current also. Okay. So I have to always make sure to operate it at the maximum power point. That is one very important thing. Similarly, if the device is open circuited, that is VO is now, let us say, 0.55 volts, somewhere here, or maybe 0.25, 525, somewhere here, 5. Power is still 0 because the current here is 0. Okay. So at the knee point, okay, at this knee point, basically, output voltage is nearly, so V out is 0.44 volts nearly, and IO over here is, let us say, output current is, as we have said, 65, nearly 60 milliamperes, and output voltage is 0.44 volts. So you can find out how much power it delivers. What is power? VO into IO. Can somebody work this out? So 28.4 milliwatt. This is the power that is generated out of this device. So 28, nearly 28.5 milliwatt, 28.4 milliwatt is a very small power. Okay. So we have to make arrays of these solar cells. At the same time, to get the maximum power output, you need to have it operated at this maximum power point. Okay. This is a very important consideration. So when we are supposed to make an array of such a kind of device, what we can do, we can simply, so this is basically the symbol again. It's just like your photodiode. So we make an array out of this. So, for example, you can have 29, 29 series connected cells. That is in one column, and we can have 18 parallel groups. Okay, this gives about 13 volts. So I can generate about 13 volts from it. You can calculate it, and then you can charge a battery, goes through a diode, like this. So this is a 12-volt battery. So this is how you will be able to use the solar cell. Now solar cells come in two different types. One is called as the monolithic. Just a second. As I was saying, they come in two types: mono crystalline and polycrystalline. These are the two types. Monocrystalline gives better efficiency, but so better efficiency. By the way, how do you define the efficiency of a solar cell? What is efficiency, by the way? Guys, am I audible? Hello.
Yes, sir.
So it is expected that maximum possible solar energy is converted into. So this is electrical energy. So maximum possible solar energy is converted into electrical energy. It cannot be 100%. Forget about 100%. Efficiency is nearly 19% only up to this point. And that is the reason why solar cells or solar energy has not been widely used so far. Okay, it has been adopted by many for many applications, but still there is a wide scope of improvement here. Okay, so monocrystalline give better efficiency, but their cost is high. Polycrystalline lower efficiency, slightly lower efficiency, but low cost. Okay, so for those who are interested more into solar cells, they can consult better sources. Okay, so that was the solar cell or the photovoltaic cell. Now we'll talk about the optocouplers, also known as opto isolators. Now many times it is required that you have to have separate grounds. Let me give you an example. For example, in sensitive circuit, if you are driving some kind of a, let us say, there is something called as a microprocessor, let us, or microcontroller. Now don't worry about what exactly is a microcontroller. if some of you have been access to, have been working with Arduino, you will be in a slightly better position to know what is a microcontroller. So microcontroller is a small microcomputer which can drive that we have to use a transistor, maybe a relay. Okay, let me just use a bigger diagram so that it will not be confusing. So if I want to switch on a motor using a microcontroller, for example, what normally is done, you have a microcontroller like this. You have a GPIO which you are going to control. GPIO means general purpose input output pin. So here I'll be using a transistor as a switch, and then I'll be using a relay to switch on and off the motor. Now this will be connected to the motor. A DC motor, let us take, and you have, let us say, the power supply, whatever is there, okay, or a battery. I mean, it's a power source like this. Now, many times you want this ground. See, this is a different ground. So as soon as this becomes high, the transistor turns on, the relay is switched, and now the new relay position becomes like this. It gets contacted, and the circuit gets completed like this. The motor starts rotating. Okay, that is how you control a motor. Here, the connection is lost. Okay. Now, sometimes what people do is they have set the same kind of power supply also, or same kind of, maybe different power supply, but they use this itself as the ground point. So this ground and this ground are same. Now, essentially, what happens many times is that we're going to discuss this more in detail when we go for grounding. Many times, so it happens that my motor is basically an inductive load. Please remember, even if I show it like this, in reality, it is going to be connected via a single wire, both of these, obviously. And then you are going to call this as the ground. So it essentially becomes this. Now, when you have an inductive load, and whenever, so this is, you can call this as an inductor. So we have already studied the characteristic of an inductor. What is the characteristic of an inductor? Yes. B equal to minus L d by dt of I. So some kind of back EMF will be generated, voltage across the inductor or the coil will be generated, and this will depend on the rate at which you are switching the current flowing through the motor, that is your inductor, as necessary. So a large negative current or a large negative voltage will be generated. So if this was the earlier scenario, large negative back EMF, as we say, will be generated. And this back EMF, as you can see, so this becomes, actually this becomes negative. I mean, this, here we have a negative voltage, positive voltage here, and here becomes a negative voltage. So you have a negative spike here. And this may have, because this is also having the same ground, this may have a detrimental effect on the microcontroller itself. This is one reason. So inductive kickback or back EMF gets coupled to this system, and it may destroy this microcontroller, which is very sensitive to voltages, because this voltage can be very high. It depends on the rate at which you are switching the current. So while switching the motor on and off, these kinds of inductive kickbacks will be coupled back to the system, and this will be very dangerous. Your microcontroller may get destroyed permanently. Okay. At the same time, you'll see that sometimes the return current also is same, because the return current path is also same. Okay, and that also may create problems. What kind of problems, we'll see more in details when we go for grounding and shielding. That is the unit number 6. So what is the remedy to that? Is it possible for me to isolate somehow these two circuits? Guys, are you able to understand to this point? Hello?
Yes, sir.
So somehow we want to isolate this. What is the best method of isolation? The simple or best method of isolation is that we can have separate grounds or return paths. So instead of having the same return path, I can simply have separate return paths. If I mark it like this and mark it like this, these two are separate grounds. So this part of the system, which is normally called as the high voltage or high voltage side. Your motor can be, run by a different, it can be even AC, which is 230 volts and so on and so on. And this is the low voltage side. So if I want to isolate this, I have to make the grounds separate. And the best way of doing that is using a device called as optocoupler. Okay. So what does this optocoupler do? We'll see that, but before that, let us see what is an optocoupler. So an optocoupler also known as opto isolator, plays a very important part in such a kind of scenario. So it is essentially made up of, so it is made up of a phototransistor plus an LED, which is combined in a single package. Okay. So when current flows through the LED, if you look at the package itself, things will be clear to you. I'll draw the package. It's available in some sort of a package, an integrated circuit. So you have an LED, you have a transistor, phototransistor, and you have coupling. So this is your LED, and this LED light falls onto the base of the transistor. Alright. So this is inside one package which is hermetically sealed, and it is covered so that it is isolated from the ambient light. Okay, so it is all dark. Alright. So when current flows through the LED, Now you can use this as a switch where by simply turning on the LED, phototransistor is turned on. Or you can even use a linear kind of signal coupling. Okay. Now, since the signal coupling is via light, because of this, that is, the coupling is optical. So we have very high degree of electrical isolation. Okay, you can have different ground here. You can have different ground here. Okay, so we have a tremendously high degree of electrical isolation. Okay, so that is the reason why this device is also called as opto coupler or opto isolator. Okay, so in our scenario, let us first of all see the specification of this device. So you have two different parts: input stage and output stage. So here you have IF. This is concerned with diode. So forward current, maximum forward current that you can pass through the diode. BF max, that is the maximum forward voltage at a particular value of IF, which is, let us say, for example, 20 milliamperes, and the maximum reverse voltage which you can apply across the diode. At the output stage, we have VCE max, that is maximum voltage that you can apply across the collector and emitter. IC max, power dissipation maximum. Saturation voltage, we see SAT, and you have ICEO, which is dark, in dark. So let us see what are the typical values. IF is 60 milliamperes, VF is 1.5 volts, reverse is 3 volts. Please note this, it is very small. VCE is 30 volts. This is 150 milliamperes, maximum possible current, about 150 milliwatt. VC SAT is 0.2 volts, and dark current is 50 nanoampere. So these are the specifications of a typical opto-isolator. In addition to that, there is one more important specification: input stage, output stage, and the coupling between them. So when I see out, that is when IF as 10 milliamperes, T on, that is maximum time it takes to turn on, and maximum time it takes to turn off, and isolation voltage. This is 5 milliamperes, let us say. Then you have 2.5 microseconds, 4 microseconds, and isolation voltage is 7,500 volts. So it is in kilovolts. What do you mean by that? Means if you apply maximum difference of 7.5 kilovolts between these two, then only this will break down. Okay, so you have a tremendously high isolation voltage. So you don't get any coupling. in the reverse direction. Okay. If you look at the application, so you have okay, I'll just put a different. So this is the LED. I will drive it with a transistor like this. Then I have, this is your supply VCC1, and you have the opto isolator. This is VCC2, and you may have the output like this. And this is your output supply. Remember that even though the base is there as a pin, it is not used many times. This is never used. So this thing is never used. This pin, it is left open. So this is how you can, okay. So you have a ground here like this, and you have a different ground. You can have a different ground like this. So this is how you can have the isolation between the two circuits. All right, guys, is it clear to all of you?
Yes, sir.
Okay. So with that, we finish unit number 5. Uh, there is one topic which is remaining from unit number 3, I guess. So let me first of all finish that too today. So remaining part of unit number 3, which is the Zener diode. Okay. So in conventional diode, PN junction diode, if you see the characteristics, this is V, this is I. Forward characteristics is like this, but the reverse characteristics, you can see that it is like this, and then at a certain point you can see that it, so for a larger voltage it literally breaks down. This value is very large, like 50 volts, 100 volts, and so on. So when what we can say is that when in PN junction diode, junction breakdown is observed.
Hello, sir.
Who's that? Some kid is interested in our lecture. See, okay. Observed when a reverse breakdown of the reverse voltage is sufficiently large. We have seen this why mechanism also, why it happens. Okay, so it's a
Not audible.
device to break down at a certain voltage. So breakdown can be utilized because this breakdown, if you see carefully, that voltage at this point is fairly constant. So I can say that the breakdown voltage is fairly constant. And we can utilize this breakdown provided you control the current flowing through the diode properly, limit the current flowing through the diode in the reverse direction properly, and of course you can have some ways in which you can program, or let us say build a device, design a device to have breakdowns at certain voltages. Okay, now this kind of diodes are called as Zener diodes. Now there are two mechanisms basically why the breakdown occurs. Okay, two mechanisms of breakdown. Now if the depletion region is narrow, guys, am I audible?
Yes, sir.
There was a call drop. Just a moment. Let me share the screen again. Okay, I was telling you about two different types of mechanisms. Is the OneNote page visible to all of you? Hello.
Yes, sir. No.
So there are two mechanisms of breakdown. Now, if the depletion region so if you look at a reverse bias junction, PN junction, so we have a depletion region. Okay. When I reverse bias this. Okay, so if the depletion region is very narrow, the depletion region is very narrow, the electric field strength, that is the electric lines of force, electric field strength, which is measured in volts per meter. As you can see, since the distance is very small, depletion region is very small, is narrow. This electric field strength E will be very high. Okay, and this is sufficient to cause electrons to break away from atoms. Okay, so obviously depletion region does have atoms, no doubt about that, but there are no free charge carriers. Now because of this electric field, the electrons which are in the covalent, tightly bound in the covalent bonds, they may get ripped off, okay, because of this electric field. And so suddenly large number of electrons will be available in this depletion region, and it will no longer be an insulator, okay, it will become a conductor. Now this type of ionization, what is essentially happening is ionization because of electric field is called as Zener effect or Zener breakdown. Okay, this is one type of mechanism where breakdown can occur. Okay. Second, if the depletion region is too wide, means that I go on increasing the reverse bias, so it becomes too wide. Like this. Now electrons in the reverse saturation current, as you can see that there are some minority charge carriers and some current, small current is going to flow over there, which we call as the reverse saturation current. Now enough energy, sufficient energy can be given to these electrons or holes wherever they are in that particular region as minority charge carriers. They cause other electrons to break free. So if this sufficient energy is given, let us say we have electron here, okay, and you have this atoms. I can show this atom as a different. Okay, so we have the atoms here. There are no free electrons, but these electrons are bound to these atoms, tightly bound to these atoms. They are not free. Here you may have holes, whatever. So this electron, which is actually a minority charge carrier, and it is crossing over into this region, if it is given sufficient energy, this will knock off this electron. So it will knock off this electron. This electron, in sense, will knock off another electron. Okay. So this, of course, will be free. It will generate 2 electrons. This will generate 4 electrons. And this is what kind of reaction you have is an avalanche. So large number of electrons will suddenly be made free and they will be available for conduction. Okay. So electrons, let us say, or let us generated due to collisions. Okay. Is called as ionization by collision. Okay. And this is called as avalanche breakdown. So we have two different mechanisms, Zener breakdown and avalanche breakdown. Remember the two different mechanisms are different or separate. Now, avalanche is generally created Guys, am I audible? Hello?
Yes,
Yes, sir.
yes, sir.
Yeah, there was again a call drop. So you have this symbol for the Zener diode. Okay. So this is again the cathode, and this is again the anode. Right. Now, if you look at the characteristics of Zener, let us quickly see. So this is the forward voltage. This is the Zener voltage. Let us call it as VZ now. Let us call it as the reverse voltage VR. Keep the same terminology. This is the forward current IF. This is the reverse current IR. So if you look at the Zener characteristics, so the breakdown point or the region where you are getting the breakdown is this, that is BZ. Now you can create diodes, you can design diodes with different Zener breakdowns or breakdown voltages. This point is very important. This is called as IZ knee point. I mean, this is called as a knee point, and the current at that is called as at that level is called as a knee point, IZ knee. And you have some maximum value, IZ max. You should not exceed this IZ max. Normally, we have using it ideally at somewhere as which is called as IZ test. Okay. Now, what is the peculiarity that you see here? Okay, let me just use some different color and okay. So, what is the peculiarity that you see? Yes, anyone? First of all, the diode is to be used in the breakdown region. In the forward region, again, it acts like a diode, so it is not used like that. It is never used in this region. It is used as a breakdown diode. So, what is the peculiarity that you see here? What you see is that after it achieves the breakdown, this Vz, that is voltage across the zener, is fairly constant irrespective of the current flowing through it. Are you able to understand this, guys?
Yes.
Hello. So if I have some kind of an unregulated power supply, means your voltage is changing. Say for example, it changes from 7 volts to 12 volts, this output, and I want only exactly 5 volts. I don't want this to change, even if your input voltage changes. So what I can do is I can use a Zener diode and place my load across it. So what will happen? After breakdown, the voltage across the diode will always be, let us say if this Vz is 5 volts. This will always be 5 volts, and the voltage across your load will be constant 5 volts. But again, you have to make sure that the Zener diode breaks down. Then only it will have 5 volts across it. So this can give rise to what is called as a voltage regulator. Of course, you have to use a series resistance over here. Otherwise, it is possible that this particular rating Iz max may be exceeded and the Zener diode may get damaged because of excessive heat dissipation because of high current. All right. So this is one very typical application, a typical application of the Zener diode. Very, very important. Again, you can see that there is a slight slope here. I mean, if you look at this, so this will be your delta Vz, right? And this entire thing will be delta Iz or I. Guys, hello.
Yes, sir.
Yeah, there was an internet failure here. Anyways, we have crossed our time limit, so I will end the meeting. We'll continue in the next lecture.